Thank you all for coming tonight. I want to introduce our speaker only briefly because I myself am just getting to know him. He has an extended background which I cannot elaborate on. So Father, if you would give us a little summary of all the amazing things you've done in your life up to this point, that would be very helpful. I'll spare you. We are honored tonight to have as our speaker Father Robert Spitzer, who is a good Jesuit. And yes, there are such men. And I kid, Father, I kid. And Father is going to talk to us tonight about the intersection of faith and science. So if I could ask you to come up here, please, Father. And please, for my benefit as well as for everybody here, please give us a little background of yourself. Thank you.
Well, I don't want to bore you with details about my biography, but I have written on this subject, and if I'd like to promote shamelessly a book, New Proofs for the Existence of God, Contributions of Contemporary Physics and Philosophy. Yeah. Okay. Good. So, essentially, this book gives a good detailed interpretation and explanation of a lot of the concepts I'm going to be going through with you tonight. I was president of Gonzaga University, which is in Spokane, Washington, for quite some time. That was probably from 1998 to 2009 for 11 years. Prior to that, I was at Georgetown University, and I taught there for 8 years. And I noticed a couple of my Georgetown friends and students who are here tonight. And so wonderful being with all of you. And I'm just going to really get to the content of my talk tonight because I think it's an important talk. It's a talk that I think we need to hear in the culture because there are a lot of people who basically are viewing things in a completely different direction. And a lot of people who are trying to convince others that science and faith are somehow contradictory to one another. Before I begin, I just want to make 3 methodological points really clear in this area. The first point is science cannot disprove God, everybody. That's not possible. And the reason it's not possible is because scientific evidence must be observed. Scientific evidence is empirical. It has to be seen. Now, if you can't observe something, can't measure it, you can't experiment for it, you can't deduce it from empirical data, it's not scientific evidence. Now, here's the problem with observable evidence. It has to come from within our universe. Yeah, you can't see anything outside of, you can't observe anything outside. We have a thing called the event horizon that you can't get beyond. And here's the problem with God. He's beyond the universe. How can you use evidence that must come from within the universe to disprove a being who by definition must transcend the universe? Answer, it cannot be done. Simply can't be done. And by the way, it's a lot harder to disprove things with empirical data than to prove them. For example, if I want to prove there's an alien out there, all I have to do is observe one. It's done. Try and disprove the existence of aliens by observational method. Why, you'd have to go throughout the entire universe and you'd have to observe everything that there was to observe, know that you had the power to observe everything that was in principle observable, and then notice after your exhaustive search that none were there. This is very difficult to do. So for all intents and purposes, anyone who tells you that science can disprove God is simply wrong. I had a little debate with Stephen Hawking on the Larry King Show about 3 years ago. And during that debate, Stephen made a remarkable statement. He said, get this now, science knows knows enough about the universe so that we can know with certainty that the universe doesn't need a creator. It doesn't need to be created by God. That statement is incoherent. And on the basis of scientific methodology, this is why it's an incoherent statement. Science is an inductive method. That means it goes from specific, particular observations and then moves to a theory which unifies these specific observations as best we know how. Do we know whether this theory encompasses all the observations that need to be encompassed in order to have a complete theory, a complete explanation of everything about everything in the universe? No, we don't. We never know whether our theories are complete. Why don't we know that? Because scientists don't know what they don't know until they have discovered it. Let me repeat that. Scientists don't know what they don't know until they have discovered it. In other words, because it's an empirical discipline, because you have to observe the data, you don't know whether you've observed all the data you need to observe in order to have a complete theory. How could you know it until you've observed everything about everything? And how would you know that you've observed everything about everything, even if you had observed it? You don't know. This is an incoherent statement. No scientist can, with any credibility, make that statement. We know enough about the universe to know it doesn't need a creator. But of course, there are other reasons for thinking that that is not right. And that is that there's three big areas of evidence. Three areas of evidence that actually show the opposite. Now, if you want me to try and go through this, I hope you haven't had too much beer. But I'm going to try and go right through this really quickly with you. And let's divide it into three kinds. Space-time geometry proofs, entropy, and anthropic coincidences. Space-time geometry proofs, entropy, and anthropic coincidences. Let's just talk a little bit about each one of these things. And then, of course, I think you're going to see that the scientific evidence doesn't point away from a beginning. The scientific evidence actually points toward a beginning of the universe. And a beginning, as we'll see in just a moment. I mean, if we actually can prove, if we can actually use scientific evidence to show that there wasn't just a beginning of our universe, but even a beginning of maybe a hypothetical multiverse. Maybe I could find a theorem which actually shows that all multiverses require a beginning. And by the way, I do have that theorem. It's called the Borda-Vilenkin-Guth theorem. We'll talk about it in just a moment. By the way, a theorem is a proof. A theory is a unification of observable data. A theorem is like a proof you learned in geometry. A theory is my way of constructing the empirical data to explain the world as I know it. Theories and theorems are very different. Theorems are much to be preferred. Now, the key thing is, let's talk about space-time geometry proofs first. Then we'll talk about entropy, talk about anthropic coincidences. And then we can see maybe science has gotten to a point where we can actually start talking about the beginning of physical reality itself. Whether physical reality is a multiverse, and of course we don't know whether there's a multiverse out there. There might be one. But we know one thing about multiverses, they're inflationary. And as we'll see in a moment, they have to have a beginning. Maybe the universe is a universe in the higher dimensional space of string theory. The 11-dimensional space of string theory. And it supports something really, really strange, like two 3-dimensional membranes colliding within a four-dimensional bulk space-time and spitting out new universes like sparks every time the collision takes place in 11-dimensional space-time? Possibly. But even that requires a beginning, as we shall see in a moment. Ooh, things are getting weird. What if science could really get very, very close to showing that every known configuration, multiverse, higher dimensional space universe, bouncing universe, right? The universe expanding and contracting, expanding and contracting. Every single one of those configurations requires a beginning, such that physical reality itself required a beginning. Then you would be getting really close to showing a beginning of physical time itself. And if you could show a beginning of physical time itself, follow me through these 3 little steps in this proof. Step number 1. If physical reality itself must have a beginning, and time itself, physical time itself must have a beginning, then prior to the beginning of physical time, prior to the beginning of physical reality was nothing. There was no physical reality in existence. In fact, there's no prior. The only way you can use prior is as a linguistic expression to refer to a hypothetical state which couldn't possibly exist. Literally, there was nothing physical out there prior, fictionally, to this beginning. Now that's an interesting thought, because we know actually 2 things about nothing. The first thing we know about nothing is that nothing is not something. We know that nothing is not like space, empty space. You can have more or less of empty space. Empty space is dimensional, it's orientable. But you can't have more or less of nothing because it's nothing. I mean, the same thing holds true. Is nothing really a very, very low, a zero energy state in a false quantum fluctuation? No, it's not. Because the false vacuum fluctuation exists, even though there's no energy manifest in it in a particular moment. It's like my bank account. Frequently, the balance is 0. But that doesn't mean that the bank account and the bank don't exist. Hello? The point is clear. Nothing is nothing. Don't be sneaking something into nothing. Now, second thing we know about nothing is that the only thing it can do is nothing. Nothing can only do nothing. Or as the great Parmenides, the great first metaphysician prior to Plato, once said it, from nothing only nothing comes. The second part of our little proof then, so if we get to a point where we have a beginning of physical reality, prior to which physical reality and physical time is nothing, then we know one other thing. That state couldn't do anything. The only thing it could do is nothing, because it is nothing. But that leads us to a third step. If prior to the beginning the universe was nothing and only could do nothing, then it could not have moved itself from nothing to something by itself, because it was nothing and could only do nothing. But that leads to a stunning conclusion. Everyone, if you really have a state where physical reality was nothing and could only do nothing and couldn't move itself from nothing to something by itself, then something else transcending physical reality something non-physical, something trans-physical, something above universes and physical realities in all their states, something transcending physical reality had to move physical reality from nothing to something. And that something else sounds like a transcendent creator to me. Call that, in simple, God. Now, you're thinking to yourself, Spencer, you better come up with some good evidence for this. Because what you're saying is that science is coming so close to establishing a beginning of physical reality that we're getting to the point of actually seeing science pointing to a metaphysical reality, a transphysical reality, namely a creator outside of universal space-time and symmetry. And I'm saying yes. That's where it is today. Why is there so much ink spilled on the notion of nothing? Much ado about nothing. In today's journals of physics, not philosophy, of physics. Because there are a lot of physicists out there worried about God at the end of the equation. That's why. So what is the evidence? Let's take space-time geometry proofs first. A space-time geometry proof, right? Space-time, don't confuse space-time with just emptiness, right? Space-time are dynamic fields. Space is what we call a contemporaneous field, a contemporaneous continuum. And time is a non-contemporaneous continuum. They're dynamic fields. They interact with mass energy. So space-time, these characteristics of space-time, you can actually make proofs whether space-time will completely converge in on itself, what might be called a singularity. You can make proofs of whether a singularity must exist or not. And if a singularity exists, that's a beginning of space-time itself. So you can actually make other kinds of space-time geometry proofs, which I won't get into today. But it might be interesting just to pause for a moment and learn a little history. Who do you think, by the way, came up with the Big Bang Theory? Who discovered the Big Bang Theory for the very first time in 1927? Yeah, it was Father Georges Lemaitre. That's right, a Belgian priest who basically went to MIT. And of course, he was a colleague of Einstein's. And then there was a problem called the extra, you don't want to know this, but it's called the recessional velocities of extragalactic nebulae. But the main thing is, Lemaitre resolved it. But he resolved it by postulating what seemed to Einstein to be an absurd theory, that the universe was literally blowing up like a balloon, or like a loaf of raisin bread, where literally the raisins were all moving away from each other because the bread in between the raisins was expanding and stretching and getting larger. Lemaitre was well aware that the general theory of relativity held that space was a dynamic field and time was a dynamic field. And because space and time were dynamic fields, literally space as a whole could stretch, it could grow, it had properties. And what Lemaitre showed is if you could actually show, what was going on is the further away a galaxy is, the faster it's traveling away from us. And so, of course, Lemaitre needed to explain that, and I'm not going to get into that today. But there's a very nice explanation of it in that book, New Proofs for the Existence of God. And of course, if you want to, or you can go to our website, magicenter.com. Just go to, all free, magicenter.com. Just go to that online encyclopedia. Nice explanation. But here's the deal. These space-time geometry proofs can establish a singularity or other reasons for a beginning of space-time, either because of what's called infinite space-time curvature to a point, that's a singularity, or for other reasons. Now, Stephen Hawking and Roger Penrose came up with the first so-called singularity explanations way back in 1968. But of course, Alan Guth, the father of inflationary theory, kind of wrecked Hawking's proof. Because the way one of these proofs work, right, is if condition A, condition B, condition C, and condition D are correct for our universe or other physical universes, then those universes will have to have a beginning of space-time. See what I'm saying? Well, one of the conditions in Hawking's proof, the third condition, actually got disproven by inflationary theory. So it was thought for a while that all the singularity equations just went bust. But that all changed. And in 1993, two physicists by the name of Arvind Borda, an Indian physicist over at the University of California, Santa Barbara, and Alexander Vilenkin, a Russian physicist who was the director of the Institute of Cosmology at Tufts University in Boston, got together and created a new proof of a beginning, a new singularity theorem on the basis of inflationary theories. And what they showed is that all inflationary theory universes, and by the way, every multiverse, you can't have a multiverse without inflation. You guys, if you have a sense of what a multiverse is a hypothetical entity. It's like a big mega universe. And the big mega universe is coughing out these little bubble universes all the time. And our universe is just one of the little bubble universes. And there's trillions and trillions and trillions of other little bubble universes. Very inconvenient if you want to try and avoid creation. Except for one problem. In 1993, Borda and Vilenkin came along and showed that every inflationary model universe has to have a beginning. And then they turned right around and showed that every multiverse has to be inflationary. Therefore, every multiverse is going to need a beginning. Exactly. So already we begin to see this idea of the beginning of physical reality. Whether our universe is the extent of physical reality or not, maybe there is a multiverse, maybe there's not. We don't know, but we know one thing: if there is one, it has a beginning. Now, all of a sudden, and starting in 1993, all of a sudden we begin to see that the world is changing. Then in 1999, a guy by the name of Alan Guth comes along, and he's the father of inflationary theory. And what he does is he kind of projects outwards all of the known inflationary model universes that we have, and all the extrapolations from those models of inflationary universes. And this is what he comes to the conclusion of in 1999. He says, if you look at any inflationary model universe or an extrapolation from them, every single one of them can be eternal into the future. But none of them can be eternal into the past. Every single one of them requires a beginning. So now the evidence is kind of tightening in. And then, of course, later we see that they have even a more expansive theorem. So Borda, Vilenkin, and Guth, by the way, has the High Chair of Cosmology at MIT. And he joined up with Arvind Borda and Alexander Vilenkin and formed what today is called the Borda, Vilenkin, and Guth proof, or the so-called BVG theorem. Borda, Vilenkin, and Guth theorem. And this particular theorem, it's so elegant, so elegant that you can actually apply it not only to multiverses, you can actually apply it to universes in the higher dimensional space of string theory. You can actually apply it to every single bouncing universe scenario. Expanding, contracting, and you can use this to show that every one of those universal or physical configurations of a universe must have a beginning. Why so? Because it only has one condition. No more if condition A, condition B, condition C, and condition D hold, then there must be a beginning. Only one condition need apply. And of course that one condition, no, not of course, the one condition is that the average Hubble expansion, a Hubble expansion is the expansion rate of the universe as a whole, that the average Hubble expansion be greater than 0 no matter how small. This is a really easy condition for almost every single universal configuration to meet. There's only one universal configuration that will not meet that condition, and that's a perfectly static universe. And we'll talk about that in just a moment. But let me just get through the BDG theorem for just a second. In 2003, once this is established, now, by the way, during the Q&A, if you want to know how this works, I can give it to you very quickly in 5 steps. I was just over at USC the other night, and I just did it, and I blocked it out, so you can kind of get the blurb method. But it's a very easy proof to understand non-mathematically. That's why it's so good. But let's just say for a moment that you can prove definitively that every single universe, every multiverse, every universe in the higher dimensional space or string theory, every single expanding universe, every single universe that's a bouncing universe, every single one of them must meet the requirement that an average Hubble expansion be greater than 0, and therefore all of them must have a beginning. If you really meet that requirement, if that's the case, then for all intents and purposes, we are getting scientifically this close to showing the beginning of physical reality itself. In fact, if we can eliminate the static universe hypothesis, right, the one hypothesis that does not conform or meet the requirement of an average Hubble expansion being greater than 0, if you can eliminate that, then of course we are really, really, really close to showing a beginning of physical reality itself. And remember, if we show that, remember that prior to that, there is no physical time. And if there's no physical time, and prior to that, the entire physical reality is nothing. And if physical reality is nothing, the only thing it could do is nothing. And the only thing it could do is nothing, and it couldn't have moved itself from nothing to something, because the only thing it could do is nothing. And therefore something else would have had to have done it, and therefore you're looking right in the face of God. This is an important consideration. So does the static universe hypothesis hold up? Can you literally have, right, you can't have infinite number of bounces. That's not going to work because BVG theorem will disprove it. You can't have a multiverse going on infinitely back in time. Multiverse will BVG theorem will disprove. Can't have higher dimensional string theory universe. BVG theorem will disprove it. You can get the data from the book if you want to get into it in detail, or my new book called Clues to Our Transcendent Nature from Experience and Reason. But the key thing is, how about that static universe hypothesis? Think about it for just 2 seconds, logically. You don't need to know any quantum mechanics. By the way, Alexander Valenkin has disproved this with quantum mechanics already. But let's say you don't know any quantum mechanics. Is there something wrong with a static universe that goes back infinitely in time? But one day it exploded into the Big Bang as we know it 13.8 billion years ago, plus or minus 100 million years. Is there something wrong with that? Absolutely there's something wrong with that. Just think of this logically for 1 minute. Any physical condition which could exist for an infinite amount of time, an eternity, already an eternity, that could exist for an infinite amount of time, must be perfectly stable. If it weren't perfectly stable, it wouldn't exist in a perfect static way for an infinite amount of time, I can assure you. But wait a minute. That universe one day expanded 13.8 billion years ago. That universe exploded and expanded. It decayed. Its quote-unquote static nature decayed into something completely different and exploded. In quantum theory, we just say it's metastable. It's not perfectly stable. It has something in it that is undermining its intrinsic stability. But wait a minute. If it expanded, exploded into the Big Bang and it's metastable, then how could it have been perfectly stable for an infinite amount of time? Because that would mean that this so-called static universe is perfectly stable and not perfectly stable in the same respect in the same place and time, which is a what? Big contradiction. What do you have there? I have a perfectly and perfectly stable universe. It's illogical. It's just not quantum mechanically unsound. It's illogical. This is a very interesting place to be, ladies and gentlemen, since 2003. Now we're getting to the point of looking at a beginning of physical reality itself. And as Alexander, by the way, Alexander Vilenkin, Stephen Hawking in his book, The Grand Design, he forgot to mention the Board of Vilenkin and Guth proof. How did that happen? Could it be he didn't know it? No, I don't think so. Could it be that he's written an essay disproving it or showing its inadequacies? No such essay exists. He forgot it. He forgot the whole Board of Vilenkin and Guth proof. Either that, or he culpably left it out. And that's not very intellectually honest, to be honest with you. My point being that Alexander Vilenkin went to Stephen Hawking's 70th birthday party in 2012, and he read this paper, Why Physicists Cannot Avoid a Creation. Here is the final sort of line, and you can also see it in his book, his 2006 book, Many Universes. Vilenkin says it this way: it is said that a good argument will convince a reasonable person, and that a proof will convince even an unreasonable one. And the proof, of course, is the Board of Vilenkin and Guth proof. Now that the proof is in place, and that includes the disproof of a static universe, now that the proof is in place, cosmologists and physicists can no longer hide behind the possibility of a past eternal universe. There is no escape. They must confront the reality of a beginning. Lisa Grossman, who was covering the event for the New York Times, called it the worst birthday present ever. The point I'm trying to get to is this. We are at a very special point in physics. And if people don't culpably ignore the evidence, we have a very interesting intersection between natural sciences and faith, originally opened up for the debate by Father Georges Lemaitre in 1927, and now finding itself on the most expansive levels in the Board of Vilenkin and Guth proof, and also in the 1993 Board of Vilenkin proof, the 1999 Guth modeling, to be very, very close to showing a beginning of physical reality. There's a second kind of evidence. I'm going to grossly oversimplify it for you. It's called entropy. Entropy is a measure of disorder in the universe. And I know what you're thinking, but just take all your thinking and wipe it out for just a second. Pretend like disequilibrium is order and equilibrium is bad. It's disorder. So we want, in our universe, lots of disequilibrium. Disequilibrium of temperature, for example, so that there's hot burning stars and cold interstellar space. We want disequilibrium of pressure and disequilibrium of particle distribution. As many disequilibriums as we can get, because when we have disequilibrium, those physical systems can do work. They can do something, but a physical system at equilibrium can't do anything. It's a useless physical system, and we call that heat death when finally a physical system reaches thermodynamic equilibrium. Now, just think then of these facts. Every single time a physical system does some work, it's going to lose just a little bit of its order. It's going to lose a little bit of its disequilibrium. So every time it does some work, it's going to lose. It's just going to move closer to equilibrium. It's going to move closer to disorder. So that if a physical system existed for an infinite amount of time, what should it be today? Perfectly disordered, perfect state of equilibrium, incapable of doing anything. You sort of with me? Okay. Now let's say that the universe, or even a multiverse, or even a universe in the higher dimensional space of string theory, because of course, you don't have to, right? Entropy is not a physical law alone. Entropy is basically a statistical law. And the reason is disequilibrium, or what we call order, is far, 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 far more improbable than disorder or equilibrium. Everything is tending toward equilibrium. Every time work is done, the system moves to equilibrium. So for purely statistical reasons, we can say that our universe, as a physical system, is running down. It's like winding up one of those, walking toys with the keys. You wind up the spring mechanism. But that spring mechanism, when it's all wound up, it's in a state of disequilibrium. And it can do a lot of work. But eventually, as it spins and spins and spins, it moves toward equilibrium, and finally the little toy stops. Now, in the same way, if our universe has been around for an infinite amount of time, stars burning, planets forming, and physicists busily thinking about it, then I can assure you that today our universe would be dead, just like that wind-up toy. It would use up all of its disequilibrium, be incapable of doing anything. It would be dead. In fact, we know that, quite frankly, we probably only have between 1 trillion to 30 trillion years left before we reach complete thermodynamic equilibrium in the universe. We know that already. We're not going to last forever, everybody. So, for all intents and purposes, sorry to say. And moreover, by the way, as we're kind of reflecting on this matter, there's so much dark energy in the universe right now. The universe is not going to collapse in on itself. The bouncing universe hypothesis has gone bye-bye. I mean, it's pretty much gone. So all intents and purposes, we're heading right here between 1 to 30 trillion. And by the way, we're not ever going to make it to 1 trillion years. Because in a half a trillion years, practically every star in our galaxy will run out of enough gases to produce heat anyway. So you don't even have to worry about it. We're dead on arrival. For all intents and purposes, though, descending from that miserable thought, what we do have is this to consider. Let's suppose we say that we're in a universal configuration, a multiversal configuration, or any other physical configuration. For purely probabilistic statistical reasons, we can predict that that universe will be completely run down in an infinite amount of time. And if that is the case, then of course, our universe today should be completely run down. But the inconvenient fact is that our universe is not completely run down. There are still many stars burning, many planets forming, and many physicists thinking about it. There's all kinds of work taking place in the universe, which leads us to suspect something is amiss. Perhaps our universe, or a multiverse, once again from a completely different data set, had a beginning. Now, for a long time, people began to think, well, maybe in a universal collapse, you get a restart in entropy. But that ain't going to work, because in a universal collapse, what happens, according to Roger Penrose, is as the universe moves toward a state of singularity, the entropy level goes up by a factor of 10 to the 80th times what it was in an expansive phase. So in other words, you're rushing towards thermodynamic equilibrium in a universal collapse, and then these two physicists, Banks and Fischler, show that essentially once you get toward a chaos state nearing the singularity, the entire universe will be called what we call a black crunch. The entire universe, just a 10 to the minus 33 seconds prior to hitting the point of the crunch, would literally be at thermodynamic equilibrium. That's not going to help you. How are we going to get out of the entropy problem? Well, you know what Einstein said about entropy? All other laws in the universe may one day be changed. Indeed, the entire general theory of relativity may one day be modified, but not entropy. For entropy does not exist on the basis of physical properties alone, but merely statistical ones. What I'm trying to say is we now have two huge groups of evidence that are leading to the same conclusion. The space-time geometry proofs of Borda-Vilenkin from 1993, the Alan Guth modeling in 1999, and of course the 2003 Borda-Vilenkin and Guth proof, which only has a single condition, and the complete debunking of the static universe hypothesis, indicating a very probable beginning of physical reality. It's not a proof, but it's a clear, indication, right, that there might well have been a beginning of physical reality itself. Multiverse, higher dimensional space universe, whatever you want to conceive of. And now entropy is doing the very same thing. The latest discoveries are Jacob Bekenstein's equations about entropy taking place in a black hole, Roger Penrose studies, Banks and Fischler's studies. It's now getting to the point where entropy is looking like a very convincing establishment of a beginning of physical reality itself, which should give us pause. Because if such a beginning exists, then I believe it's a beginning of physical time, which implies some kind of creative force outside of space and time itself, a creative force that is not physical reality itself, completely transcends it, and has the power to create the whole of physical reality in a single moment, including physical time itself. It's interesting. Interesting point. Third thing I just want to get into very quickly, anthropic coincidences. This is a very important area because anthropic coincidences, they don't really point to a beginning of the universe. What they point to is the intelligence of the creator itself. So what you're dealing with is you have this huge transcendent creative force if you can prove a beginning of physical reality. What you're now talking about is something quite different, the intelligence of that creative force outside of space and time. So is that force conscious? Is it intelligent? Is it mind-like, as we sometimes refer to it? And the answer seems to be, yes it is. And we think of that for two reasons. First, we go back to that thought about entropy. Recall for a moment that high entropy is high disorder. Equilibrium is high disorder. It's very easy to obtain. It's very probable because all physical systems tend towards it. So it's only going to be very probable. Low entropy, however, is highly, highly, highly improbable. And the low entropy that we experience in our universe at the Big Bang is so exceedingly improbable, as we'll see in a moment, that it could not be said to have occurred by pure chance. There's this guy, Roger Penrose, a very important physicist at Oxford University. He basically came up with what's called Penrose's number. And it's actually a very easy number to deal with. And Penrose's number, what he did was he showed the odds against low entropy at the beginning of the universe. And all you have to do is take the total number of baryons in the universe. It's like the protons and neutrons, and you combine them all up. And there's only 10 to the 80th baryons worth of mass in our universe, more or less. And you take the 10 to the 80th times the entropy per baryon, which is 10 to the 43. And so 10 to the 80th times 10 to the 43 is 10 to the 123. And then you take that entropy, and of course it's the logarithm of the phase space requirements for entropy, so you just take the exponential, and the odds of that happening is 10 raised to the 10 raised to the 123 to 1 against. Let me repeat that number. That's a double exponent. That's 10 raised to the 10 raised again to the 123 to 1 against low entropy in our universe. Now, if I reduce that to a single exponent, that'd be a 10, and in the exponent a 1 followed by 123 zeros. In other words, the exponent would be a trillion, 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 trillion. Now, if you reduce that to a single number without an exponent, where every zero was 10-point type, our solar system could not hold that number. It is the same odds as a monkey typing the corpus of Shakespeare by random tapping of the keys in a single trot. You walk into the room, you say to the monkey, type me Shakespeare. The monkey says it gladly, give him a cigarette, some food, he begins randomly tapping on the keys. You come back a couple weeks later, you're shocked to see Macbeth in perfect folio form, and the Hamlet on top of it. And you begin to think to yourself, this is highly improbable. Now you know what poor Roger Penrose was thinking, which made him blurt out. Well, the creator had to select an exceedingly small portion, namely the low entropy portion of total phase space possibility to get a universe even remotely resembling our own. Creator, he said, because it seemed impossible to explain by pure chance. The monkeys typing Shakespeare by random tapping on the keys in a single stride, not likely to happen. This is not entertainable as a scientific hypothesis. Now, as we'll see in a moment, the multiverse hypothesis is going to come in very handy as a possible explanation. Because, right, if you have every single time you have a bubble universe coughing out of a multiverse, guess with me? It's a new roll of the dice. You get to reset the entropy again, and reset the entropy again, reset the entropy again. And maybe one time, you're going to go, instead of getting something that's one of those old, highly probable equilibrium possibilities, you're going to get a highly, highly, highly improbable disequilibrium possibility that just happens by pure chance. If you have 10 to the 10 to the 123 universes, maybe you could. Possibly. And so maybe that is a physical explanation. Might be. We'll have to talk about it in a moment. Which is more reasonable? Which is more responsible? In just a moment. But let's back up for a second and see some other instances of what's called anthropic coincidences. Now, why should you stick with anthropic coincidences? Steve Meyer is my very good friend, the author of Darwin's Doubt and a group of other people. But you have to be really careful about using so-called anthropic arguments that happen after the Big Bang. And the reason is you don't want to create a God in the gaps argument. You don't want to say, hey, this is so improbable, it must have been God. Because if you do it after the Big Bang, the scientists could come back at you and say, but we might not know all the natural causes affecting this operation, and so maybe tomorrow we'll discover a whole new natural cause that affected this operation, and you didn't need God in order to explain this highly improbable occurrence that we just understand in a very, very limited way right now, and therefore your argument is completely flawed because you did not consider all the natural explanations. Pardon me. So the key thing then is, let's now go back to the Big Bang. Why is that so special? Just remember this. The Big Bang is a boundary to natural causation. Once you're at the Big Bang, even if there was a period prior to the Big Bang, even if there was a multiverse, even if there was a quantum gravitational string theoretical configuration prior to the Big Bang, It is absolutely causally discontinuous from the Big Bang, which follows it, which is what we call a general theory of relativity universe. The best kind of argument for anthropic coincidence is always going to be a Big Bang argument, because nobody can appeal to a prior natural cause. There wasn't one. And that makes it really interesting for physicists as well as everyone else. Okay, let's take a look at constants for 1 minute. I don't want to overdo my time here. But we've got these 20 numbers in our universe called constants. These numbers are really, they're called physical constants or universal constants. And these numbers control all the laws of physics in the universe. So we have, the equations of physics that describe what we call the laws of nature, right? The laws of physical reality. And each of these equations has constants in it. Those constants make these things real. So there's real minimums, and real maximums, and real ratios, real numbers, right? What are some of these 20 constants, right? And many of you know the speed of light constant, right? 186,200 miles per second, 300,000 kilometers per second, right? You can't have a physical velocity higher than the speed of light, 300,000 kilometers per second. Why is it that amount? Don't ask that question. We don't know. Because there's nothing special about 300,000 kilometers per second. Could have been 400, could have been anything. But it is 300,000, and that's very significant. Oh, by the way, we have 4 forces in our universe, right? We have the strong nuclear force, we have the gravitational force, the electromagnetic force, and the weak force. Each one of those forces has constants associated with it. So the strong nuclear force has the strong nuclear force coupling constant. The weak force has the weak force constant. The electromagnetic force has 3 constants associated with it. The mass of the proton, the mass of the electron, the electromagnetic charge. The gravitational force is the gravitational constant, and so forth. Some of you have heard about Hubble's constant, which was previously Lemaitre's constant, named after that Belgian priest, right? Hubble's constant for the transforming what we call the recessional velocity from the distance that an object is from a particular moving body. So, of course, you've got Planck's constant. Remember Planck's constant, converting frequencies of energy, right? And so forth. So we've got 20 of these numbers. Well, they're just numbers, but they're really special numbers. Now, bear with me for just 2 seconds. If those numbers could have been anything, just like the instrument unit, those numbers could have been anything at the Big Bang. But here's the rub, everybody. If they had just been a little higher than their actual values, or a little smidge lower than their actual values, within a very narrow window of opportunity, then life as, not just life as we know it, all possible life forms would have been impossible. Let me repeat that. All possible life forms would have been impossible. So how can you predict this? Look, I'll just give you 3 examples so you get the point. If you altered the weak force constant or the gravitational force constant by 1 part in 10 to the 50th from their actual values, either higher or lower, right? 1 part in 10 to the 50th, you know what I'm talking about? A decimal point, 49 zeros, and a 1. Like a really small fraction, higher or lower from the actual values that they have, then either the universe would have been continuously exploding in its expansion, which, by the way, would have been very bad for all life forms, or the universe would have collapsed into a black hole, where the mass density of the universe would have been making a gravitational attraction approaching infinity, crushing everything into not just a spaghetti, but into a point of 10 to the minus 33 centimeters. Exceedingly bad for life forms. You mean we averted complete cosmological disaster by 1 part in 10 to the 50th, higher or lower, in these 2 constants? Yeah, it's precisely what I'm saying. How are you going to explain that? There's only two possibilities. You either go the supernatural route and say something really smart did it, or you go the natural route. There were a lot of universes in the multiverse, and trillions upon trillions of bubble universes. But remember, we are now back to the monkey typing Shakespeare again. We gotta have a lot of bubble universes to explain just one, ours. Let's give you 2 examples. I'll wrap this whole thing up. Another example, if you took the following 4 constants and modified them by only 1 part in 10 to the 39th, higher or lower, the gravitational constant, the mass of the proton, the mass of the electron, or the electromagnetic charge. You alter by 1 part in 10 to the 39th, higher or lower, then either every star in our universe would have been a blue giant, or every star in our universe would have been a red dwarf. Yes, the truth of the matter is, we have the majority of our stars in the universe are thermodynamically convective. They're stably convective. Yet we are literally, the gates of thermodynamic instability, of convective instability, are literally right on us. If every star in our universe were a blue giant, everything would fry, which is very bad for life forms. And if everything in our universe were a red dwarf, everything would freeze. There wouldn't even be enough sun to give a Hawaiian a ticket. For all intents and purposes, we would literally, you mean we averted complete disaster, for all life forms by 1 part in 10 to the 39th, and the mass of proton, mass of electromagnetic charge and gravity? Yep, that's what I'm saying. I mean, how do you explain that? At the Big Bang, when those constants could have been anything at all. Multiverse, smart guy. Take your pick. Third, last thing. If you modify the strong nuclear force coupling constant by 2% higher, there would be no hydrogen in our universe. No hydrogen for nuclear fuel, no hydrogen for water, very bad for life forms. And if you made the strong nuclear force coupling constant 2% lower, there would be no element heavier than hydrogen. Iron, carbon, very bad for life forms. The entire universe would be hydrogen, which would have no possibility of combining into complex molecules, which can give rise to life forms. Yiko, you mean we averted complete? Wow, look at the coincidences. There was a wonderful, did you see that picture in Scientific American where the 2 snowmen are talking to each other, and the one snowman is saying to the other one, "Don't be absurd. Of course we originated not with any intelligence, but the sheer accumulation randomly of snowflakes." This is what we're dealing with. Okay, here's the rub, you guys. You're going to have to choose one way or another. If you go the multiverse explanation, here are the 3 problems you will have to explain if you're going to say it's an adequate explanation of order and fine-tuning of the constants of our universe. Problem number 1, every multiverse has to have a beginning according to the Board of Elayton and Booth proof, so it couldn't go back infinitely. There's always going to have to be a finite number of possibilities. But that's not going to, it still can go back a really long time, and you could maybe have 10 to the 10 to the 10 to the 10 to the 123 universes, right? You could maybe do that. That's a lot of zeros. I don't think our whole universe could hold those zeros, but that's okay. I mean, nevertheless, you can do it. Number 2, it's a violation of Occam's razor. Now, Occam's razor is not a scientific law. It's what we call a canon. It's the way things tend to operate. Nature tends to be elegant. Nature tends to choose the simplest way. nature tends not to choose convoluted routes and all kinds of bloviated assumptions in order to explain itself. Nature's elegant. But I mean, as Paul Davies said, if you need to postulate trillions upon trillions upon trillions upon trillions of universes just to explain one our own, well, that's rather like bringing excess baggage to cosmic extremes. But it's still not a disproof. That's not the nail in the coffin of the multiverse. Here's the real problem. Every single known multiverse model and hypothesis today itself requires substantial fine-tuning, ordering in its initial assumptions, its initial constants, its initial conditions. Listen, we have the Linde, what's called chaotic fractal universe, right? Multiverse, excuse me. Now, the Linde chaotic fractal multiverse, originally was just thought it could be sporadic. But then, Albajetti and Life two physicists kind of said, that won't work, because if you have sporadic bubble universes being created, then the gravitational fields of those bubble universes are going to interfere with one another in the huge multiverse. And when they interfere with one another, eventually they're going to draw closer to one another and collide with one another. And when you have bubble universes like ours colliding with one another, the entire space-time configuration of that universe is wiggling like a jello, which is exceedingly bad for life forms. So poor old, Linde has to postulate a slow roll of bubble universes in ordered symmetrical fashion, which requires tons of fine-tuning in the initial conditions and constants of that multiverse. Here's the problem, everybody. Every single multiverse model requires fine-tuning in the initial conditions and constants of that multiverse. Meaning that we do not have a solution to the fine-tuning of our universe. All we have done is successfully moved it back one step. Back to the level of the multiverse, where the quandary once again presents itself. And yet, that's not an adequate explanation. This might lead us to think for just a moment. If we combine the two sources of evidence for a beginning of physical reality itself, the space-time geometry proofs and the entropy evidence, and you combine it with those anthropic coincidences, you may get very, very close to a very supernatural, not just power, but a supernatural mind. I'll just conclude with two quotes from two well-known physicists. The first is from Sir Fred Hoyle. Sir Fred Hoyle used to be, by the way, the atheistic gadfly of the physics community. He always had an atheistic response for every time theism reared its ugly head, quote unquote. Right? But at one point, his partner, William Fowler, came in and said, Fred, I'm just taking a look here at the numbers, the odds against having the resonance levels of oxygen, beryllium, carbon, and helium be the exact levels that they need to be in order to get an abundance of carbon in the universe necessary for life forms. And of course, Hoyle goes, what are you talking about? So he shows him these equations, and at least the lore goes that Hoyle went into his office for 3 days, and this is the quote he came up with. I'm not kidding. It seems to me that there are no blind forces worth speaking about. The odds against an abundance of carbon in the universe requires that some super-calculating, super-intellect monkey with the constants of physics and those of chemistry and biology as well. I consider this conclusion to be beyond the shadow of a doubt. He later went on to say, the odds of getting an abundance of carbon in the universe by pure chance are the same as a tornado sweeping through a junkyard, assembling a Boeing 747 ready for flight. The point I get to is, yes, at the end of the day, we're still left with belief, Science will not definitively prove an intelligent creator, but science can give a lot of evidence in favor of an intelligent creator. And it can do it in a way that applies holistically, not only to our universes, but other universal and multiversal configurations of physical reality. We are getting to a point where the nexus between creation and the nexus between creation and science is reaching a pinnacle. I conclude with this quote from Robert Jastrow in his book God and the Astronomers. He was the founding director of NASA's Goddard Institute of Space Studies, and he basically said, look, the scientists unshackled themselves from the domain of superstition and took on a methodology of strict measurement, empirical observation, and mathematical quantification of the data, and began to assemble the cliffs of knowledge. When they came to the final precipice, they pushed themselves over and discovered a band of theologians there awaiting them for centuries. Thank you very, very much. I kind of went over into my Q&A time, and I don't want to...
It's okay, Father.
Yeah, call on people, and I'll take Q&A for a while, and please, if you need a beer, please refresh yourselves. It's a heavy go, I know. Oh, okay.
So during your
Can I have your attention, please? If you want to ask Father a question, please come line up here so that way you can ask your question into the microphone and we can all hear you. So please come forward if you have questions.
So you cited Alan Guth as one of the people who created this theorem that basically should make us assured of the fact that the universe had a beginning. But Guth himself would not ascribe that beginning to a creator. He would say something along the lines of a quantum fluctuation in a vacuum created it. And so I was wondering, what do you have to say about this alternate theory of quantum fluctuation?
The quantum fluctuation theory, this is the one I was just talking about. Here's the problem with the quantum fluctuation hypothesis. It really doesn't get you out of his own theorem, because at the end of the day, the quantum fluctuation really is an expansive condition, even though it lasts for a minimal amount of time. The point, of course, is several physicists have pointed this out to you. And by the way, Alexander Vilenkin himself has tried to seek shelter in the quantum fluctuation hypothesis, but now has admitted that what he has done in so doing is actually required himself, basically contradicted himself in so doing. There's a wonderful analysis of this in an article that's online written by a guy named William Lane Craig. And Craig is a kind of an apologist, but he's a knowledgeable one with his physicist Jim Sinclair. And if you want to see the whole quantum fluctuation hypothesis as a possible beginning point debunked from a physical and logical point of view, I believe that all you need to do is put into your Google search engine Craig Vilenkin quantum fluctuation. You'll get the article. It's all there, free of charge. You can make your own decision, but I think at this juncture, Jim Sinclair definitely has Guth and Vilenkin back against the wall. Good question.
Everybody in the back that's talking, can you please keep it down, please, so we can have Father answer questions and the rest of us can hear this. Please keep your talking to a whisper, please. Hello, people in the back that are still talking. Shh. Okay, who wanted to ask the next question? Amanda, come on up.
Is multiverse theory always improbable, or just from an atheistic perspective?
Improbable, yeah. Well, multiverses are not improbable. Multiverses can actually, they're possible. There's only three problems with the multiverse. Number one, they do have to have a beginning. Number two, they will require fine-tuning. That is to say, they're going to require ordering of their initial conditions and constants. So with those two things in mind, I wouldn't say a multiverse is improbable. A multiverse is just not going to do the explaining that needs to be done in order to get out of either a beginning or an intelligence at the end of the singularity, as it were. Good question.
Are there any other questions?
Well, we could do part two at some other point. We could do evolution. No.
Thank you, Father. How are you doing? So I had a question. There's an atheist, Dan Barker, who had an interesting thing to say about kind of the presupposition that, you know, there's these constants like gravity that can actually be altered in any way. And he says that what evidence do we have to presuppose that it can even be altered, that it can have some sort of numerical difference?
Yeah, a constant actually is not a physical law at all. It's just the numbers that govern those physical laws. And so the problem is, it's a complete crapshoot at the beginning of the Big Bang. What are going to be the numbers that are going to regulate, right, the laws of the universe? So in other words, it's not like the numbers have a reality. The numbers actually are an occurrence that take place along with the physical laws. Now the problem is, there's nothing intrinsic to say 300 million kilometers per second that requires that it must take place when the physical laws of the universe take place, right? Remember, if you're going to postulate a naturalistic theory, you have to postulate that there wasn't a mind necessitating these numbers, right? They just simply occur. And the laws of physics just simply occur. And if that's the case, in science, right, we say there's nothing necessary about a number. There's nothing necessary about a law, right? They're what we call not necessary truths, they are factual truths. And anyone who says that these constants, therefore, are necessary would have to prove that a specific number is necessary, which even, quite frankly, Aristotle 2,400 years ago would have laughed the very proposition of the academic stage. And that proof does not exist. You can't prove that a specific number has any more necessity than any other number, right? They're all wonderful numbers. It just so happens that the ones we believe are there. In any case, I thank you very much for your kind attention, and I know you would want to get back to the enjoyment and social nature of the evening, but thanks for your kind attention.